Welcome to example 4. This is a question that involves the equal potential surfaces within a capacitor. So, suppose we have a parallel plate capacitor, as described here, and they're separated by 6 millimeters from the top plate and the bottom plate with a potential difference of 24 volts. We're asked to let the negative charge plate be 0 volts as indicated down here, and the top plate to be a positive 24 volt potential. In this question, we're just simply asked to do two things: to sketch the electric field lines and the equipotential lines for this diagram. And specifically for the equipotential lines, we're asked to show the 24, 18, 12, 6, and 0 potential lines. Because this is a parallel plate capacitor, we know that this electric field, is uniform and perpendicular to the plates. And they would go from the direction of the positive plate to the negative plate. And since they're uniform, it means they have to be equally spaced and parallel. And so there you go. There's the electric field lines drawn parallel and equally spaced going from positive to negative. Now let's look at the equal potential surfaces. So the negative plate is really an equal potential surface. It's already shown. This plate along here is really 0 volts. And the positive plate is also another equal potential surface, so that's 24 volts. We can indicate that, but that's already shown right here and here. What we need to do is actually plot the 18 volt, 12 volt, and the 6 volt potential line. As you move from the 24 potential line to the 0 potential line, since this is a uniform field, the equal potential lines will drop off equally as you move down. So we'll go say 24 to 22 to 20 and so forth. Let's find out how many millimeters you have to go, or how many volts you get for every millimeter of spacing. Remember that equation that the electric field is equal to the negative change in potential divided by the distance along the electric field line. So in this particular case, if we go from the very top plate to the very bottom plate, we have a potential difference of 24 volts, and this is covered over a distance of 6 millimeters. So that means that you have a drop of 4 volts for every millimeter. Okay, but we really want to drop from 24 volts down to, say, 18 volts. So how many would it be in 6 volts? If you were to go for 6 volts, that means that you would have 6 volts for every 1.5 millimeters. That would mean essentially if you started, say, at the 0 volt line, you could say that if you went up 1.5 millimeters, you would have the 6 volt line. And then if you went up another 1.5 millimeters, that would be 3 millimeters, then you would have the 12 volt line. And then if you went up another 1.5 millimeters here, all right, then you'll have the 18 volt line. And then the last 1.5 millimeters will bring you up to 24 volts. So let's show that now. And there you go. There's the solution of the problem. These are the equal potential lines here at 18 volts and then 12 volts and 6 volts, each separated by 1.5 millimeters between each line. And you notice that these lines are equally spaced, just like the electric field lines are equally spaced, because if you have a uniform electric field, you've got then a uniform equal potential lines as well. If the electric field lines were not uniform and they got closer together, then so would the equal potential lines as well. Okay, and that's it for example number 4.